What's up? What's up? We are on page 107 right now. Let's just get right into the lesson. Pause the screen if you need it. Again, pause the screen if you need it. Okay, so here we are. We're going to be working with dominoes. So we worked with dominoes today in class. So I just want you guys to be able to see that. So I got some dominoes here, okay? I'm not going to set up like a billion of them because we don't have a lot of space. So I'm going to set some up real quick. So the idea of this, if you read on page 107, you're supposed to set up some dominoes in a line. So kind of the way that you see here. Now, it doesn't matter if it's curved or straight. So you could do a little bit of this or that, right? Like this or that. I'm doing a little bit of that, right? And what you're going to, your objective is to knock them all down. Now the thing is, you can go quickly like I'm going, but you gotta kind of be steady, right? Because if not, it's easily to knock them down, and students observe that in class. So you set them up. Now remember, in order to set them up, we're using energy, right? So we're inputting energy already into the system by the way we have them set up. Then we still need more energy input into the system because, as you can see currently, nothing is actually happening. But once I input some energy right here, actually, I guess I'll put it over here so you guys can see that. Whoa! And actually, a domino went way off the actual table. So I was able to knock them all down. And what happened what did you observe when the first one? And you observed that this domino hit that domino, and then it started a chain reaction. And the kinetic energy was passed from one domino to the next. Now they want to see, is this an example of kinetic energy? Well, since kinetic energy is the energy of motion, then the answer to that would be, hopefully you're saying yes, that is kinetic energy, because the dominoes were in motion and we're passing the kinetic energy from inside me, right? So, and then pushing it into this system here. Now, could we stop the domino? So I'm going to see if we can do this, if we can stop the last domino from falling. Now, one idea is this. We're going to put a bunch of dominoes at the very end and see if we can get them not to fall down. All right, let's just take a look. Yep. So it worked. So we added a lot of mass here so that way there wasn't enough force to push them all the way down. As you can see, it's going to take more than just a regular amount of force to push them all down. So that actually did work. So that was one way that people did it. Some people just spread them out. Now, another thing they're saying is, can we put more kinetic energy in the middle? And how we're going to try to do this, we're going to see if we can make this happen, is we're going to try and spread the dominoes out that are at the ends and put the ones in the beginning much closer together and see if we can actually see a little bit of a speed up or slow down. Can we add more kinetic energy in this area? Let's see. Ooh, that didn't even work. Okay, I saw it a little bit slower, sped up. I wasn't able to, it was so fast, I wasn't able to quite see it at the end. What did you guys see? You can go back and replay that video and see what you see. And since it's on YouTube, you actually can slow it down. And the last thing is, what observations did you make in the activity? Some of them were that some of the things that I observed in the activity and watching students do this was, one, people had different designs. Also, some people kept knocking their dominoes over. Some people were not placing their dominoes close enough, right? Some people were able to make their dominoes go much faster than others just based on a spatial location they were located to each other. So I noticed quite a few different things, right? So again, just get all those things right there on page number 107. And if you don't, you can do all this stuff at home with your own dominoes. And if you don't have it, then you can use what you just observed right there. All right, let's keep it pushing to page number 1. Now, I wanted to show this. I showed this in class. But if I show this on YouTube, Mr. Beast gonna be like, we can't do that. So we're not showing this. We going to the next. Nope, we're not showing that. Anyway, if you do want to see that, just look up Mr. Beast and dominoes and you can check that out. And you can see Mr. Beast using dominoes just like this to crush a 7-Eleven. Wild times. Hey, if Mr. Beast ever watches this video, you should let me use some of your stuff for educational purposes, sir. All right. Anyway, next, moving on. So we should be on page 109. Again, page 109. We're going to review the math and then go over the graphing. That's what we're going to do. Again, review the math and then go over the graphing. I'm going to go ahead and pull that up because I actually have it right here. And I was able to get some people just gave me their data, and in class on Friday we reviewed one of the data's rows and we went through running. So I just wanted to make sure that everyone was on the same page with this. Is to say, okay, we have the time for racer 1, the time for racer 2, and the time for racer 3, and what we're gonna do is we're gonna add them all up. So we add those all up, right? And I will show those calculations here. I'll do that part again, which is totally fine. No big deal. So I'm going to add all them jokers up. So then I got 2.27 plus 3.3 plus 3.3. So I add all them up, and then whoops, that got messed up. Okay, so 2.27, that was the first one, plus 3.3 plus 3.3 is equal to, and then we're going to take that number and we're going to divide it by 3. That's kind of what you see here. And then that gives us 2.95, and we rounded it to 3, right? Because the 9.5 would round to a 3. So that's what we got. Again, we added those numbers together, and then we divided by 3, and then we ended up with rounding it to 3 or 3.0. Okay, so now what we're going to do is we're going to calculate the speed, and that's what we're going to do right here is we're calculating the speed. And to calculate the speed, it is distance divided by time, and that's what you see here. The distance is 10 meters. So if you look at this thing here, oh, I don't like how thick that thing is. Boom, let's go. Let's put it to 1. Bam. That way the writing will be a little bit easier. All right, so this is the distance right here. Bam, which is 10 for all of them because we all went 10 meters in the experiment. So the distance divided by time, and the time comes from right here, right? So that is where we got the time from. Now, I do want to make sure this is clear because I saw a lot of people calculating the speed incorrectly. When you're putting that in there, whenever you say divided by, that first number needs to go first. So distance divided by time, the distance is 10, so that should be entered into the calculator first. Divided by, which is this line right here, is the divided by, and then by the time, which is 3. Okay, and you got to make sure to put it in that way, and you end up with 3.3. We rounded it because we didn't need all these to 3.3. That's how we got this 3.3. You see, it's the same one that's in the calculator. Now it's time to finish it off. Now, the formula for kinetic energy, if you look at it, it's right here, 0.5 times mass times the velocity squared. Okay, now couple of things. Speed and velocity mathematically are equal to the same thing. Again, I'm going to say this again. Speed and velocity are equal to the same thing mathematically. So when you look up here, if you look at the formula, and I'm going to go ahead and hit that with the highlighter, it actually is right there on your page that kinetic energy is equal to 1/2, which is the 0.5 mass times speed squared. All right, cool. Now let's go ahead and go back down here, and if we take a look here, 0.5, which is our half, right? And then our mass, which is 50, is, if you look inside of this right here, our mass is actually located right here. Boom. So our mass for this data table, we're using 50, so that's where I got the 50 from. And then as far as the v squared, which is going to be the speed squared, okay, that's the 3.3. And again, the speed is coming directly from what we calculate here in this column, okay? All right. So then I'm gonna show you guys how to put all of that in the calculator. Now, if you have the blue calculator, that one does not have a square function, but just as a reminder, whenever you're squaring something, it's just that number times itself. So just know that. So if you're like, I don't have the squared function, totally fine. 3.3 times 3.3 is 3.3 squared. Okay, cool. And then I'm just going to work backwards through the problem since I'm already kind of running through it. So I did that part first, then I'm going to say times 50, okay? And then I'm going to say times, and then the 0.5. So 0.5. and then I end up with 272.25, and that's how I got rounded to the 0.3. Okay, now I'm just going to show you also, if you do have the squared function, you could just go 0.5 times 50 times 3.3, and then here's the squaring right here, squared. If you look, you can see that that's everything right there, and then you'll just say equal to, and then again you come up with the same answer. So again, 3.3 times 3.3 is 3.3 squared, so they're equal to each other. That's why you see either way that you put it into the calculator, you get to the same answer. Okay, so again, you get to the same answer. So I just want to make sure that all of that is clear. Okay, cool. Now that we have all of these, let's just take a look over here. And so how I got the rest of these maths, you're trying to go through, calculate the rest of them, and I just got them from students. So I just pulled from students' data, okay? And then as we go over here, how I got the X and the Y, got the data for that, is I said, okay, well, what is going to be on my X-axis? Right here it says speed is on my X-axis, right? So that's X, okay? All right, cool. And then it says that on my Y-axis is going to be kinetic energy. So if you look down here in the data, I already have that labeled. So my X these are all my X coordinates, and these right here are going to be my Y coordinates. So the first coordinate, right, I'm just going to write this out so maybe it might be easier for you to see, is going to be 0.5 comma 6.3. And again, I pull that directly from this data table. So my next coordinate is going to be 1.4 comma 49, and my last coordinate is going to be 3.3 comma 2.723. That is my last coordinate. So those are the coordinates I'm going to graph. So as far as the X-axis is concerned, I probably need a numbering system, because that's the next thing I need to do, is my minimum and maximum, that is going to go from 0 to probably 4, okay? Again, I'm not going to try and use any crazy numbers, so I'm just going to go like this because I think that this might work. So 1, 2, 3, and then on the fourth one, I'm going to put a 1. So that's like 0.25, 0.5, 0.75, 1. And then this would be like 1.5, and this will over here be 2. So then 1, 2, 3, and then this is going to be 2 right here. Okay, and then 1, 2, 3, and this is going to be 3 right here, and I think that that's going to work out. And then 1, 2, 3, and this is going to be 4. That is more than enough to fit all of my data in there, if you look, because my data only goes to 3.3. Now for my y-axis, it's got to go from 0 to at least like 300, because I have a 272. Some of you guys might have like a 400. So if, depending on how big your numbers are, depends on how you should actually make the range on your axis. So I'm going to use the same similar numbering system. So I'm going to go 1, 2, 3, and then instead of putting a 1, I'm going to put 100. And then I'm going to go 1, 2, 3, and then I'm going to put a 200. And then I'm going to go 1, 2, 3, and then I'm going to put a 300. And again, the numbering system is very similar, but instead of counting by ones, I'm counting by hundreds. So 1, 2, 3, and this is going to end up being 400. Okay. Now, just to go, like this would be 25, 50, 75, 100. So each line on the y-axis is an increment of 25 joules for kinetic energy. So now it's time to just go ahead and start the graphing. So I'm going to zoom in as much as I can. The first thing is going to be a 0.5, which is right here, and then 6, which is really low, because this, if this is 25 right here, only maybe a fourth of that. So that's way down there. All right, cool. And then I'm going to go ahead and label that thing. So I'm going to put it on purple, and that thing is walking heel to toe. Okay. All right. Now, the way that you would actually like graph this thing, and this part's going to be hard because I always have a very difficult time like trying to just make the line straight, is I would go from the origin point through there. So I'm going to see if I can just make a line right through there. Okay, that worked out okay. That worked out okay. Now let's go to graph our next point. So it's 1.4 and 49. So 1 point, let me see, let me make sure. 1 point, oh yeah, 1.4. So if you, this is 1.25, this is 1.5. So it's like 1.4. And then this line right here is 50. So it's just below it. Boom. Okay. So somewhere right in there, again, it's not going to be perfect, and that's okay. So now I've got to like try and get a line from there. So I'm going to see if I can. Oh, yeah, okay. I mean, it's okay. Again, you guys will use a ruler, so yours should look a little bit straighter than mine. Okay, let's graph our last point, okay? Our last data point. And actually, let me go ahead and label this as well to say that this is walking normal. Okay, now let's go down to our last one, which is 3.3 and 272. Oh my gosh. So if this right here is 3.25, then it's just over 3.3, and then 270. This is 275 right here. So we're going to go just below that. Okay. Like right in there. Okay. Cool. And then our last one, let's just go ahead and use this orange right here. And then this one's is gonna be a little bit crazy. So I'm gonna see if I can get it to go through. Okay, that didn't work out that good. Let's go, because we wasn't. Okay. Let me see if I can. This line. Let me see if I can get something that will help me, like. You guys can't see that, but that's okay. Yeah, I think this will help me. This will help me. Your line should be straighter than mine, but you get the idea of what is supposed to be going on, okay? I tried. I'm sorry. Okay, so again, this is sort of or very close to how your graph really should be looking. Again, you will have a much straighter line than mine going through there. But that is how your graph should be mostly looking. And as you're seeing, as the speed is increasing, right? So as speed increases, right? Depending on how you're moving, you'll have to use more kinetic energy, which hopefully that makes sense to you, that the more speed that you have, you know what I mean? Then the more kinetic energy you're actually using, right? All right, y'all. Go ahead and finish these questions right here, and then go ahead and scan this thing and get it turned in. Peace. I don't know how to stop. Oh, there we go.